force between two long current carrying wires. So what's going to happen here? Imagine you have a wire that has a current coming out of the board. Then you have a wire that has current going into the board, right? What's their force going to be between each other? Are they going to repel each other or attract each other or repel each other? So it's almost as if we've gone a full circle. That's what we started the semester with, right? Plus minus Coulombs Law, K Q1 Q2 over R squared. I tell people it's almost like we took a whole journey and we start with Coulombs Law, with forces between charges. We notice that two opposite charges attract each other, right? And then two like charges repel. So we can almost call this two opposite currents. Do they attract each other or repel? Do you remember the answer to that, Daniel?
I'm not sure if they. Hold on. Let me think about it real quick.
Huh? It's okay if you don't remember, that's fine. Well, it ends up that it's opposite of how charges behave. Two opposite current carrying wires behave like two like charges. They actually repel each other. It's weird.
Yeah, I was going to say that. I'm like, yeah, I remember them repelling each other. Right?
Yeah. So in other words, they behave. The way to remember this is because most of you will remember this, of course. That's ingrained in us. But if you don't remember, just remember that it's opposite to this. Opposite to how charges behave. So if you have current going out of the board into the board, opposite currents, they will repel. If you have two like currents, they will attract. And then two like currents, they will attract. You see? Now here's why. So here's the breakdown of why. To analyze this, you say, what's the direction of the B field of this wire created at that location? So it's kind of like the same thing that we did for electric field. You say this wire creates a B field there. Let's call this wire 1. Wire 1 creates a B field there. So what's the direction of that B field? So you put your thumb out of the board and you curl it and you say, oh, the B field created there is up, right? So we'll call this B1, magnetic field due to wire 1. Then to find the force on that wire, what do? IL crossed into B, right? IL crossed into B1. So you take the current of that wire, right? So this is the second wire. You take the current of that wire times the length of that wire, right? Times the magnetic field created by this wire at that location. You see? So then you do, the current is into the board, curl it in the direction of B, and you see, repel. Now you can do the same thing for this guy. So now find the B field created here due to this. See? So the thumb into the board and then you curl it around. You see? Like that. So it's also up. Right? Now find the force on that guy, on this wire, due to that B field. So, oh man, it's almost like you could, yeah, this is better. So the wire, the current is coming out of the board, curl it in the direction of B, and there you have it. So of course, they should both repel, you know. So this is F1. Force on wire 1, force on wire 2. See, force on wire 2 is due to the current of wire 2, the length of wire 2, times the magnetic field of wire 1. And then force on wire 1 is equal to current of wire 1 times the length of wire 1 times B of wire 2. So what's the equation of this? We're going to get a similar looking equation to this, which is going to act almost like Coulombs law, right? We could say Coulombs law with quotes because there is no Coulombs law for that, but it's just, we can say it's similar. So then what's that equation going to be? F2 is going to be I2, L2. Of course, L and B are perpendicular because L is going into the board and B is this way. So L2, and then the B field created by a long wire. You see, notice that my equation only works if the wires are long. So B field created by a long wire, what's the equation for that? Mu 0 I1, right? Because the B field created by wire 1. Mu 0 I1 over 2 pi R. There you have it. That's our Coulombs law. Mu 0 I1 I2 I1 0 I1 I2 L2 over 2 pi R. Okay, so that's the force on wire 2. So what's going to be the equation for the force on wire 1? Well, similar arguments. I1 L1 mu 0 I2 over 2 pi R, and R is the distance between them. And then you have what? Mu 0 I1 I2 L1 over 2 pi R. So it's kind of like this because this is 1 over 4 pi E0, so it's kind of like similar to that. Q1, Q2, that's like I1, I2. And then the only difference, it's got a unit of length here and another unit of length. Yeah. But of course, the units of mu 0 is way different than the units of K. So it works itself out so that it's newtons again, of course. Now you might say, well, what if the lengths were slightly different? You know, what if this was long and that was long, but maybe different length? So do they repel each other with different forces? That's a legit question. But then Newton says, oh no, for every action, there is an opposite equal reaction force. So according to Newton's, these forces are action-reaction pair. So they must be the same, right? So what if one wire is 100 meters, let's say the other one is 120 meters? How do we handle that? How do we force the two forces to be the same? Right? It's a legit question. So let's say the length of this is 100 meters. So that's long enough to be able to use this equation, you know, and L2 is 120. The answer to that is, well, this equation that we're using is an approximate equation, and it works when the wire's length is long enough and their distance with each other is close enough to use this. So that's one argument to say. So then the other argument is going to be to say, technically these forces should be the same. So if they have slightly different lengths, maybe you take their average and you say 110, and then you use here, so this one, you just do 110, 110, you see. So then it's just going to be 110. Or you might even just say, forget the fact that they're different. Just make this 100 and just put 100. In other words, most problems that ask you this kind of question, they don't even give you the lengths different. They give you the lengths the same. because the forces have to be the same. But just in case they do give you different, then averaging them is probably the safest bet. Averaging the two lengths is the safest bet. No one is going to give you something like this, let's say 100 meters, 1 meter. This wire is 100 meters, this one is 1 meter, because then you couldn't even use this equation at all. One of them is short, the other one is long. Oh no, we have to do integration then, you know. So no one's going to give you that extreme. So if you look at the equation that most websites give you, they don't even write L1, L2. Force between two current carrying wires. You see, F over dl is mu0 I1 I2 over 2 pi r. Then dl is the length of the wire. Notice even in the picture, they made them the same length. You see, so they have two wires going in the same direction, right? And then they just write that way. So they don't distinguish between their lengths. But even if they did, then you could just take their average of the lengths. They're showing you here by the right-hand rule how to really analyze that. Maybe we can end with a similar problem to how we began the semester, like the pith ball problem.